Hi, my name is Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know for the Regents on the math of chemistry. Now, there's a lot of math in chemistry, and a lot of people get afraid of the math in chemistry. But really, if you know the reference table, you don't even need to be afraid because most of the formulas that you need to know are on the reference table and on table T. And we're going to talk a little bit about table T. But the first thing you need to know when you're dealing with the math of chemistry is the term the mole. Now the mole scares a lot of people because they don't really understand what it is. They learned in class that 1 mole equals 6.02 times 10 to the 23rd particles and 22.4 liters, and that doesn't make sense to them. What you need to understand is that a mole represents the amount of something, and it's abbreviated MOL. It just represents the amount. If I wanted to take the temperature of something, I would use degrees Celsius. That represents the temperature. If I wanted to take the weight of something, I'd say 10 grams. Grams would represent the mass of something. If I wanted to find the volume, 10 milliliters. Milliliters would be the volume. If I want to know how much I have of something, I could use the term moles. Now, in this equation up here, they're showing the moles. The coefficients here represent the moles of that compound. So in this case, I have 2 moles of C4H10, which happens to be butane. So I have 2 moles of butane. I have 13 moles of oxygen. I have 8 moles of carbon dioxide, and I have 10 moles of water. It just represents an amount. So don't be afraid of it. It just represents an amount. Now, you need to understand, moles we'll get back to moles in a little bit. Just make sure you understand moles represents an amount. And there's that whole thing with 6.02 times 10 to the 23rd. It's just saying that 1 mole of any gas at SDP has that many particles. Now, that's not on the Regents anymore. It used to be, and you probably learned about it in class. And we can spend a little bit more time talking about it in the chat, but I'm going to go on for now. You just need to know for right now that moles represents an amount. Now, formula mass and gram formula mass. That's the next thing you need to understand. The formula mass represents the mass on the periodic table. For example, carbon has an atomic mass on the periodic table of 12.011. Therefore, its formula mass is 12.011 AMUs, atomic mass units. So the formula mass for carbon is 12.011 AMUs. The gram formula mass of carbon is really confusing. Actually, it's so simple. The gram formula mass of carbon is 12.011 also, except it's not in AMUs. What do you think the gram formula mass of carbon is in? You guessed it, it's in grams. So the gram formula mass of carbon is 12.011 grams. Formula mass is 12.011 AMUs. Gram formula mass is 12.011 grams. Now, you sometimes have to figure out the gram formula mass or the formula mass for a compound. Let's say carbon dioxide, which is CO2. If you have to find it for CO2, well, you have to take each of the elements. Carbon has a mass of 12.011. In chemistry, when we're dealing with formula mass or gram formula mass, we round. So carbon is 12. Oxygen is 15.994. We round to 16. Now, we don't just add these up. Why? Because oxygen, there are 2 oxygens. There's 1 carbon at 12, but there are 2 oxygens. Each one is 16, so we have to multiply that by 2. So now we get 32 and 12, which equals 44. So, 2 things we could be asked. What's the formula mass of carbon dioxide? Well, the formula mass of carbon dioxide is 44 AMUs. But most of the time, we'll be asked for the gram formula mass of carbon dioxide. And the gram formula mass of carbon dioxide here is 44 grams. That represents your gram formula mass. And you need to be able to calculate the gram formula mass. And all you're doing is you're going on the periodic table and finding the mass of 1 mole of the substance, or whatever the mass is on the periodic table, represents the gram formula mass in, obviously, grams. you need to understand, and the reason we talked about formula mass and gram formula mass is dealing with mole calculations. Sometimes they ask you to calculate the number of moles. Now, it's actually quite simple, but what gets confusing is you don't remember the formula. But you don't have to remember the formula. It's on table T, but it's hidden really well, so you can't figure it out. No, it's not hidden at all. It says mole calculations. Mole calculations, you see on table T, it says the formula is moles equals given mass over the gram formula mass. Let's figure out how many moles we have, and let's do an example. Let's say we have 17 grams of carbon dioxide. So we have 17 grams of carbon dioxide. And I want to know how many moles I have. Well, remember, the formula for moles from table T is moles equals the given mass over the gram formula mass. Well, 17, what's the gram formula mass of carbon dioxide? We did it before. 12 plus 16 times 2 is 32. 12 plus 32 is 44. So it's 17 over 44. Now, we put it on our calculator, 17 divided by 44, and we get 0.386 moles. Now, a lot of people want to be able to do mole calculations in their head. For example, if we know that there's 44 grams in a mole of carbon dioxide, well, what if we have 88 grams? Well, that's twice as many grams, so we must have 2 moles, or twice as many moles. Well, that's true. And you could do that sometimes, but this works on every formula. Every single type of a problem that you do with mole calculations, this works. You take the mass you're given, put it over the gram formula mass, divide, and you get your answer. Well, could it work the other way? You may be saying, what do you mean the other way? Well, the other way is, what if I'm given the moles, and I'm asked to find the grams? Well, of course it can. Let's say they said, I have 1.87 moles of carbon dioxide. 1.87 moles. Well, the formula is moles equals given mass over gram formula mass, so the moles is 1.87. What's the given mass? We don't know. That's what we're asked to find out. We want to find out the mass. So that's our x. What's the gram formula mass? Well, we know the gram formula mass from the periodic table is 44. We set up our equation. We put the 1 here just to make it simpler. We cross multiply, and we get it's 1.87 times 44, which represents 82.28. And that represents the mass given 1.87 moles. So it's all very simple. You just have to know to go to table T and find the formula. And once you find the formula, it all becomes simple because you're just plugging it in. And that's how you find the mole calculations between grams and moles. Now again, you did a lot of mole calculations in class with particles and volume. That stuff's not on the regions. So in one sense, you're happy that it's not on the regions. And in another sense, you're saying, well, why did my teacher teach this to me? Well, the reason your teacher taught it to you is because it is chemistry. And you could know that. It will help your knowledge. We can go over that in the chat. If you have specific questions, I'll answer them. But for right now, you just have to know how to convert from moles to grams. And you're given that formula on table T, so there's nothing to memorize. The next thing we're talking about, and the next type of math problem they give on this Regents, is percent composition. Percent composition represents the percent you have within a whole substance. And the formula, again, table T, you're in luck. It says right on table T, percent composition, mass of the part over mass of the whole times 100. And it's very simple. You just have to plug it in. These are the easiest kind of questions they could give. And let's say we want to give an example using potassium chlorate. And they say, what is the percent by mass or the percent composition of oxygen in potassium chlorate? Oxygen in potassium chlorate. So you have potassium chlorate is KClO3. They want the percent by mass of oxygen in potassium chlorate. So the formula is mass of the part over the mass of the whole. Well, what's the part? Well, if they're asking for the percent by mass of oxygen, then the part is oxygen. Each oxygen from the periodic table is 16. There are 3 of them, so 16 times 3 equals 48. So the mass of the part is 48. Now you have to find the mass of the whole. And if you look on the periodic table, the mass of potassium, K, is 39. And the mass of chlorine is actually 35.5. We normally round, but for chlorine, since it's right in the middle, we round it to 35.5. So the mass of chlorine is 35.5. Now, how do we find the mass of the whole? Does that include oxygen, or is it just potassium and chlorine? Of course, the whole includes everything. So we take 39 plus 35.5 plus 48, and what do we get? We get 122.5. Part over whole times 100. We put this in our calculator. 48 divided by 122.5 multiplied by 100 equals 39%. What that means is, in potassium chlorate, 39% of potassium chlorate by mass is oxygen. And that's how you do percent composition problems that are just straight up percent by mass problems like this one was. And remember, it's mass of part over mass of a whole times 100. The other kind of percent composition problem they can ask is dealing with a hydrate. Now, a lot of students also get freaked out by the word hydrate. It's very simple. When you're thirsty and you want to get hydrated, what do? You drink water. If you're dehydrated, what does that mean? You don't have enough water. In chemistry, it's the exact same thing. Percent by mass in a hydrate. A hydrate is a crystal that contains, what do you think? Correct. It contains water. A hydrate is a crystal with water inside. And they designate it in a certain way. Let's say we have a copper sulfate crystal. It's copper sulfate. Where do you see water? You don't. You have to designate this water. So you put a dot. And let's say, in this case, there's 5 waters. That means that in this whole crystal, for every 1 mole of copper sulfate, you have 5 moles of water. And don't get thrown off by this dot. This dot does not mean times or multiply. This dot just means that it's together. There's 5 moles of water inside this copper sulfate crystal. Now, you have to find the percent by mass of water in this hydrate. And remember, percent by mass is part over whole. Percent by mass of water. Now, I do the water together. I don't do hydrogen by itself and oxygen by itself. I put them together. Water is, hydrogen is 1, and oxygen is 16. But there's 2 of them, so it's 1 times 2. So water as a whole is 18 grams, or 18 AMUs, depending on what you're dealing with. So water is 18. Now, there are 5 waters, which means 5 times 18 is the mass of the water. And that is 90. So the mass of the part, in this case, is 90 because that's the mass of the water. Well, what's the whole? We then got to do everything. Well, copper is 63.5. And remember, it's right in the middle, so in this case, copper also, we would round to 0.5. Sulfur, on the periodic table, is 32. And oxygen, we know, is 16, but there are 4 of them, so it's 16 times 4 equals 64. So we have 64, 32, and 63.5. Now, do we just add these 3 up? No, that's the most common mistake, because that's not the whole. That's just the whole copper sulfate part. You need to add up 63.5 plus 32 plus 64 plus the water, which is 90, because you multiplied it by 5. That's the whole. So 63.5 plus 32 plus 64 plus 90 equals 249.5. Mass of the part, which is water, over mass of the whole, which is the whole thing, times 100. You do it on your calculator, and you get 36%. And the whole trick there is it's not hard. The whole trick is knowing what this hydrate means and what a hydrate is. But this is a simple percent by mass of a hydrate. And there's actually one other way that they can ask percent by mass of a hydrate. And it's actually the easiest way that they could ask it, because there's really very little math involved. There's just a little bit more thinking involved. And they could say, one of the ways that you want to, if you have a hydrate, let's say you had copper sulfate with water or whatever, one of the ways you remove the water is you heat it. Because water has a different boiling point. Water is going to boil quicker than than the salt will. So what happens is, let's say you have a substance that has a mass of 4, a hydrate with a mass of 4. And then you start heating it. And you may have done this in the lab. So you start heating it. You start with a mass of 4. After 1 minute, the mass is 3.9. What does that mean? That means that some water was removed. Okay, 0.1 was removed. So we have 4. It started with 4. After a minute, it was 3.9. After 2 minutes, maybe it was 3.7. After 3 minutes, it was 3.5. After 4 minutes, it was 3.5. After 4 minutes or 5 minutes, it was 3.5. After 6, 7, 8, 9, 10 minutes, it was 3.5. Why is it a constant mass? Why is the mass not changing after you're heating it? Because all the water was removed. You had a mass of 4, but it was a constant mass at 3.5 because all the water was removed. So what was the mass of the water there? Well, if it started at 4 and it became 3.5 and all the water's gone, the water's 4 minus 3.5, which is 0.5. The mass of the part is 0.5. What was the whole? Well, let's see. What was the whole? Well, the whole is what you started with. The whole is 4. That's what you started with. And you do 0.5 over 4 times 100, and you get your percent composition, 12.5%. And that's the only other way they could ask percent by mass in a hydrate. And that's the only other way they could ask percent by mass. So you see, percent by mass is a very simple formula. There's just a couple of different ways they could ask it, but no way is hard. You just have to know it all. Another kind of way that they could ask these kind of questions, another type of math problem, and unfortunately for this one, it's not on the reference table. So you have to know this one. You have to think it through. And it's finding a molecular formula. So let's say they said a compound has a molecular mass or a formula mass of 180 AMUs and an empirical formula of CH2O. So molecular mass of 180 AMUs and an empirical formula of CH2O. And they want to find out what is the molecular formula. Now, this is a 3-step process that you need to understand. And you have to go over the 3 steps. And the first step is to find the mass of the empirical formula. Mass of the empirical formula. Well, how do you do that? You have CH2O. Well, the mass of the empirical formula, carbon from the periodic table is 12. Hydrogen is 1, but there's 2 of them, so that's 12 plus 2 is 14. Oxygen is 16, so 14 plus 16 is 30. So the mass of the empirical formula, equals 30. That's what the mass of the empirical formula is. The second step, so now that you know the mass of the empirical formula, the second step is to divide the molecular mass by the empirical mass. And let's see what that gets you, and you'll see why in a second. 180 is the mass of the whole thing, and the empirical mass is 30. 180 divided by 30 is 6. Now remember that the molecular formula represents the actual formula, and the empirical formula represents a simplified version. So you know, though, that the empirical formula, the empirical mass, is 6 times smaller than the molecular mass. Or the molecular mass is 6 times greater than the empirical mass, which means the molecular formula is 6 times greater than the empirical formula. So the third step is to multiply the subscripts from the empirical formula, you had CH2O, it's to multiply the subscripts by this number right here. So you had CH2O, and you want to multiply. You know that the molecular formula is 6 times greater, so that means everything has to be multiplied by 6. Which equals 1 times 6 is C6, 2 times 6 is H12, and O, 1 times 6 is 6. So we know that the molecular formula here is C6H12O6. Remember the 3 steps that you have to do. The first step is finding the mass of the empirical formula. The second step is dividing the molecular mass by the empirical mass to see how many times greater the molecular mass is than the empirical mass. And then the third step is to take that number and multiply the subscripts to show that the molecular formula is 6 times greater than the empirical formula. You just have to know those 3 steps. They don't ask these kind of questions that often, but when they do, now you're going to be a pro because you know how to answer it. And it's actually not that hard as long as you understand what an empirical and molecular formula is. And sometimes you could probably just figure out how to do it based on that information. But if you know the 3 steps, you'll never get it wrong. And then the last thing we have to do is the most important thing we have to do. It's the thing they ask on every single Regents they've ever given. Every Regents has a problem like this. And it's a mole-to-mole ratio. So this brings us back to our original equation. This shows, and just for simplified purposes, I'm going to tell you what this is called. This is called butane. And if you want to know how to name organic compounds, go to the concept on naming organic compounds, and you'll figure it out. But this happens to be butane. This is saying that there are 2 moles of butane, 13 moles of oxygen, 8 moles of carbon dioxide, and 10 moles of water. Now, you have to, sometimes they ask you simply, what's the ratio of butanes to oxygens? And the ratio is 2 to 13. The mole-to-mole ratio is 2 to 13. But it usually gets a little bit more complicated. If we have 2 moles of butane, how many moles of oxygen do we need? Well, according to this equation, for every 2 moles of butane, we need 13 moles of oxygen. And that produces 8 moles of carbon dioxide and 10 moles of water. That's what this equation is showing. Now, let's take it a step further. What if we had 4 moles of butane? If we had 4 moles of butane, how much oxygen would we need to react this whole thing completely? Well, if 2 moles, you need 13. If you have 4 moles, you need twice that. You need 26. And I could also say, if you have 4 moles of butane, how much carbon dioxide will I get? Well, if 2 moles gives you 8, 4 moles would give you 16. And what you did there is in your head you thought of a ratio. I'm going to tell you how to do this systematically. Every time you get a problem like this, you will know exactly what to do. And the way you know this kind of problem is they give you a formula, they give you a chemical equation, and they ask you how many moles of one of them would you have if you have a certain number of moles of another. For example, if it said, how many moles of oxygen will react completely with 4.5 moles of butane? How many moles of oxygen? This is what I want you to do. When you see how many moles of oxygen, you find out where oxygen is. Oxygen's right here. How many moles of oxygen? I want you to put an X under the oxygen, and you'll see where I'm going in a second. How many moles of oxygen, you don't know, that's X, will react completely with 4.5 moles of butane? Well, here's butane. They want to know how many moles of oxygen if you have 4.5 moles of butane. So you have X oxygen, 4.5 moles of butane. And that's what you have here. Now, you're not done. Now you take what you had originally. You originally had 2 moles of butane and 13 moles of oxygen. So what do you do with that? You put those on top. You may be saying, what are you doing? Why are you putting these numbers? And I promise you'll see. One thing I want to say before we go on is look at the whole equation. Notice, did we even mention carbon dioxide here? Or water? that part of the equation is not part of our problem because it doesn't mention it in our problem. And it doesn't relate to it, so it doesn't matter. We can leave that out for now. We're just using butane and oxygen. And what you do now is you set up a ratio. 2 moles of butane, but now you have 4.5 moles of butane, will give you 13 moles of oxygen, but now you have X moles of oxygen. So you set up a simple ratio. 2, and you see it, 2 over 4.5, excuse me, 2 over 4.5 equals, and you have it up there, 13 over X. You have the ratio there for you. This over this equals this over this. It's set up for you. The reason why I had you put them on top and the bottom is because those are the numbers in the ratio. 2 over 4.5 equals 13 over X. And you cross multiply, and you get X equal to 29.25, which means you get 29.25 moles of oxygen. And let's think about whether that makes sense. Well, you had 2 moles of butane, which gave you 13 moles of oxygen. If you had more than double it, you should have more than double the oxygens. And 29.5 is more than double 26, which is double 13. Bottom line is whether you understand and you can think about it in your head or not, I don't care. The Regents doesn't care. What the Regents does care about is that you set it up right. Whatever you have, whatever you're given in the problem, how many moles of that goes on the bottom? And if you have 4.5 moles of this, it goes on the bottom. Whatever you had originally in the equation goes on top. You just set them equal to each other, and you have a way that you will never get this question ever wrong on the Regents. Now, could they give you one substance on one side and one on the other? Of course they could. They can give you any 2 of the substances in this whole chemical reaction. But all you have to do is put the coefficients you have on top, right? Put the coefficients you have on top and what they're giving you in the problem on the bottom, and you will never, ever get it wrong. And the reason it's so important that I say this is because this is on every Regents, and you need to understand. And they only ask for mole to mole ratio on the Regents. So you only have to go from mole to mole. Well, I hope you learned a lot about the math of chemistry. There's a lot of stuff for the math of chemistry. Some of it's complicated, some of it's not, but most of it's on the reference table. Most of it's on table T. Some of it you have to memorize, but keep doing the questions. I promise. The best way to do math is to go over questions. So all the questions that relate to the math of chemistry, I want you to go over, and I want you to listen to the video explanations, and you're going to get so sick of it. You're going to be like, I know this already. I don't care. Still do it. Because the more you do it and the more it gets in your head, the better off you will be. If you're still confused, come to the chats, look over your review sheets, go over the lessons again, go over the questions again, do whatever you need to do, but make sure you know how to do the math of chemistry. I hope you learned a lot.